Welcome to lesson 8.1, 2, and 3. Today we're going to talk about chemical bonds, and we're going to start by talking about ionic bonds. First, bonds in general are just forces that hold groups of atoms together and make them function as a unit. And any energy required to break a bond is called bond energy, because in a molecule, the energy is found in the bonds of the molecule. First, let's look at ionic bonds. Ionic bonds, if you'll look at the example right here, ionic bonds are when there's an electrostatic attraction. So, for example, sodium atoms and chloride or chlorine atoms are not stable. If they come near each other, then one will gain an electron, the other will lose an electron, and when that happens, you form the sodium cation and the chloride anion, and that positive-negative interaction gives that electrostatic attraction there. So that's ionic bonding. It's just positives held together with negatives just simply because opposite charges attract, and that forms an ionic compound. Now, when you have two identical atoms, and I do apologize for the way this is scrolling, but when you have two identical atoms, what happens is you want atoms or chemistry in general wants to be at its lowest energy. So identical atoms like hydrogen in the diagram shown here will come close to each other, close to each other, close to each other until they form the lowest energy. And so if you look down here, that hydrogen-hydrogen bond length is about 0.074 nanometers, and that's where that hydrogen bond is lowest in energy. Those hydrogen atoms are sharing electrons, so they're forming a covalent bond. Covalent bonding is when two identical atoms share electrons equally. And so notice it said identical atoms there in covalent bonding, because covalent bonding is the sharing of electrons, but a truly non-polar covalent bond generally results from the attraction of two identical atoms. So hydrogen, hydrogen, fluorine, fluorine, chlorine, chlorine, and so on. Most covalent bonding is polar covalent. And polar covalent, they're still sharing electrons, but they're not sharing them equally. So just a quick concept check with the definition right there above. What type of bond is formed when electrons are unequally shared? Well, that's going to be a polar covalent bond because it says shared, so that knocks out all of the ones that say ionic, and then it says unequally, so that means it's a polar covalent bond. Electronegativity is the driving force of determining if a molecule has a polar covalent bond. And electronegativity was first analyzed by Linus Pauling, and he defined it as the ability of an atom in a molecule to attract electrons to itself. So in this example here, it says, consider a hypothetical molecule HX. If H and X have identical electronegativities, or the ability to attract electrons to itself, they'll share electrons equally. So H and H are going to have the same electronegativities, and so they're going to share electrons equally. If X has a greater electronegativity than H, the shared electrons are going to be pulled closer to the X atom, and notice that there's a charge distribution in the atom. So if you looked at the atom over a period of time, the X end is going to have somewhat of a negative charge, and the H end is going to have somewhat of a positive charge. The greater the electronegativity differences, the greater a bond moves towards an ionic component. All right. So here's Pauling's electronegativity values. Notice up here, fluorine is a 4, and down here, francium is a excuse me, a 0.7. So you'll notice you can kind of see a trend on how electronegativities increase the closer they get to fluorine, the higher the electronegativity, the higher the ability to pull electrons toward it. So when you look at a difference in electronegativity, purely covalent bond would be a 0. As polarity increases, you move towards polar, covalent, and then down in this area, you get into ionic. So if we're going to order the following bonds according to polarity, then what we're going to do is we're going to look at the differences in electronegativities. So let me shrink that just a tad so we can get both those on the same page. There we go. Okay, so in an HH bond, the difference in electronegativity is going to be 0, because if I subtract 2.1 from 2.1, I get 0. Now, oxygen, the difference between electronegativities in oxygen and hydrogen is 1.4, because you see oxygen's here, and then hydrogen's still 2.1. Chlorine hydrogen's going to be 0.9. Sulfur hydrogen is going to be 0.4. I don't know why it's not writing very well right now. Fluorine hydrogen is going to be 1.9. And so if we were to take these and order them according to polarity, the most polar is going to be FH, and it's going to be more polar than OH. It's going to be more polar than CLH, more polar than SH, more polar than HH. Okay? So that's using electronegativities to determine polarity. You can also use the periodic table. So like I said, and we're kind of leaving these out, but fluorine is the most electronegative and francium is the least electronegative. And so we can actually, I know concept check number 3 says without using the table above, and that means the electronegativity table, because if you'll notice from your notes, I inputted the periodic table here. But so we're going to use the periodic table, predict the order of increasing electronegativity in each of the following groups of elements. So we're going to look at CNO, and what happens with CNO? As you go CNO, you get closer to fluorine, and so the electronegativity is going to increase in that direction. SE, and Cl. So which one's farthest from fluorine? It's Se. So Se is the smallest. And then we have S, and then we have Cl. So it's just the proximity to fluorine is what's going to indicate the highest electronegativity. Now let's look at silicon, germanium, and tin. Silicon, germanium, and tin. Silicon is the closest, and tin is the farthest. So those are going to increase that way. And then the last one, thallium, sulfur, and germanium. So in this one, thallium is going to be the least, and then germanium, and then sulfur, according to the periodic table. Which of the following elements forms the most ionic bond with chlorine? Well, which one is the farthest from chlorine? Here's bromine, krypton, phosphorus, aluminum, and then potassium's clear over here. So the most ionic character is going to be the potassium. Okay, so when we look at these particular bonds and they have a center of positive charge and a center of negative charge, that's called a dipolar. That's called a dipolar molecule. Bonds can each be characterized as having a dipole or not having a dipole. Molecules can also be considered as polar or nonpolar based on what the specific bonds in them have. So let's say, for example, that we have an atom that has a dipole. So the carbon dioxide molecule actually looks like this. Oxygen is more polar than carbon, so the dipole goes this way in each direction. But notice what happens. Those bond polarities, those individual dipoles, cancel each other out, and so that molecule itself is a nonpolar molecule, even though it does have polar bonds. And the next page, a couple of examples. So there's that carbon dioxide molecule I just showed you. There's some planar molecules, some tetrahedral molecules. The same thing happens where we can have polar bonds, but there's no net dipole moment, so it's a nonpolar molecule. And so let's look at the examples below that table. For each of the following molecules, show the direction of the bond polarities and indicate which ones have a dipole moment. So HCl, I don't know what's going on with my pen here. HCl, the dipole moment is going to go towards the Cl because Cl is more electronegative. ClCl is not going to have a dipole because those atoms are the same. They're going to have the same pole. And then SO3, if you'll look up here, this example is SO3, and it shows there's dipoles in the bonds, but they cancel each other out. So the molecule itself is a nonpolar molecule. CH4 tetrahedral, so that's going to be very similar to this one, except the bond polarities are going to be going the other direction. But still, they're going to cancel each other out. And so it has polar bonds, but it's a nonpolar molecule. And then H2S is going to be very similar to water because it's actually a V-shaped molecule. And we'll get to that when we get to Vesper structures. And so what we have here is we have some dipole moments, but in those two particular bonds, there's nothing to cancel them out. So that's considered a polar molecule because they're not exactly 180 degrees from each other. These interactions here and here are different than these interactions here and here, and so they don't cancel each other out. So H2S is a polar molecule. All right, so let's look at these last few concept checks here. Concept check 6, which of the following is the most polar bond without being considered ionic? Okay, so ionic means metal, nonmetal, and so this one is going to be ionic because magnesium's a metal and oxygen's a nonmetal. So the most polar, so the rest of them we're combining with oxygen. Which of those atoms is the farthest from oxygen on the periodic table? Carbon, nitrogen, fluorine, or oxygen itself? So if we look back up here at the periodic table and we get rid of a few things around here, fluorine, nitrogen, and carbon. So the farthest from oxygen is going to be your carbon. And so we'll go back down here, and the most polar bond in that bunch is going to be the carbon, the carbon-oxygen bond. Which of the following is the least polar bond, yet still considered polar covalent? So again, this is not covalent, or this is not, yeah, it's an ionic bond, not covalent. This one is not going to be polar covalent. It's going to be completely covalent. And so in this example, we really need to go back up to the table because nitrogen is right next to oxygen and so is fluorine. And so let's go up to the table of electronegativities. The difference between oxygen and fluorine is 0.5. The difference between nitrogen and oxygen is 0.5. And so these two are actually tied. So it's the least polar bond, but still considered polar covalent. Which is the correct order of the following bonds in terms of decreasing polarity? So we're looking for differences in electronegativity. So that first one, we're looking at nitrogen, chlorine, phosphorus, and so on. So let's look at, so we're all bonding with chlorine, nitrogen, phosphorus, arsenic. Okay, so chlorine is here, nitrogen, phosphorus, arsenic. So which one is going to be least polar? Well, probably least polar is going to be the nitrogen chlorine because they'll have the closest electronegativities. And so are those in order of decreasing polarity? They are not because nitrogen chlorine would be on the end. And so we're looking for the one that has nitrogen chlorine on the end. So here are our two options. And then the next closest one was phosphorus, and so this is our option. Obviously, this question would be a lot easier if we had a periodic table sitting in front of them. We didn't have to scroll. In which case is the bond polarity correct? So if we're looking at bond polarity, we want to, or sorry, incorrect. We want to make sure that the most electronegative atom has the delta negative on it. So in this case, fluorine's the most electronegative atom, so this one is correct. Oxygen, most electronegative, that one is correct. Hydrogen in this example is the most electronegative because magnesium is a metal and it will always lose electrons. Iodine and chlorine, silicon and sulfur. Um, so iodine and chlorine, which one's closest to fluorine? Chlorine is closest to fluorine, so this one is the one that's incorrect. And you could also look at where they are on the position on the periodic table on that one too. Okay, all right. Thanks for listening. We will continue with lesson 8.4 and on and next time.